we need to sketch the graph of this function using the given guidelines. The guidelines, let me write them. The first part is we need to find the domain of the function. Okay, so domain means the x values for which this function is defined, and we know this is a rational function. This is undefined when the bottom is 0. So when does the bottom become 0? Let's see that. So x square minus 4 is 0 when x equals plus minus 2, because 2 squared 4 minus 4 0. Negative 2 squared is also 4 minus 4 0. So domain is all reals except x plus minus 2. Okay, basically all reals except 2 and negative 2. That's the domain. And this function is already simplified form. We can factor the bottom, but we cannot factor the top. So in fact x equals 2 and negative 2 will be vertical asymptotes. We'll write that in a moment. And the guideline says part B, find the intercepts. Okay, intercepts. So there are 2. So we need to find x intercept. For that we plug in y equals 0. Y is same as fx equals 0. So we set the function equals 0. So 2x squared plus 1 over x squared minus 4 equals 0. Whenever we have a fraction equals 0, bottom has no contribution, because we can always write 0 over 1 and cross multiply. That implies top equals 0. 2x squared plus 1 equals 0. Let's solve this for x. Move 1 over, negative 1, divide by 2. That implies x squared equals negative 1 over 2. But this is a false equation, because any number square is always positive. So x squared equals negative. This is false. That means we don't have any x values. So no x intercepts. So x intercepts none. So no x intercepts. So the graph of this function does not intersect x-axis. Let's find y-intercept. To find y-intercept, we plug in x equals 0. Let's plug in 0. We get 2 times 0 squared, 0 plus 1, basically 1 on the top, 0 squared 0 minus 4 on the bottom, so negative 1/4. 1/4. This is not y/4. Okay, so x is 0, y is negative 1/4. So y-intercept is 0 comma negative 1/4. The graph of this function passes through this point 0 comma negative 1/4. So, and the guideline says in part C, find asymptotes. Asymptotes. Okay, so there are, I mean, in this case we just want to find vertical asymptotes and horizontal asymptotes. So let's find vertical asymptotes. Okay, since this is a rational function and is already simplified, so x equals plus minus 2 are the vertical asymptotes. Okay, in fact, when x approaches to 2 or negative 2, this function either goes to positive infinity or negative infinity, and it blows up or goes down. That's how we find the vertical asymptotes. So vertical asymptotes are x equals plus 2 and minus 2. Now we need to find horizontal asymptotes as well, HA. That means when x goes to all the way to the right plus infinity or all the way to the negative infinity, where does the function go? So we want to find the limit when x goes to plus infinity and minus infinity. In fact, we are supposed to find two limits. Let's try both in one. Limit of this function, so 2x squared plus 1 over x squared minus 4. This limit is same as the following limit, plus minus infinity. This is a polynomial, so when x is very very big or very very small, we can just write down the leading term. Okay, it only matters with the leading term, 2x squared over x squared, leading terms, and x squared cancel, just 2, so 2. Okay, so y equals 2 is the horizontal asymptote in both sides, like when x goes to plus infinity or negative infinity. In both sides, y equals 2 is the horizontal asymptote. Okay, and the guideline says the next is okay, I was supposed to go for symmetry first, but I found asymptotes. Let's go to symmetry. Okay, doesn't matter which one comes first. Symmetry. To check if the graph has y-axis symmetry or origin symmetry, we replace this function by negative x by negative x. Okay, replace x by negative x. So we evaluate the function at negative x. So basically replace x by negative x, we get 2 times negative x quantity squared plus 1 over x squared, means negative x squared minus 4. And let's simplify. Negative x squared is same as positive x squared, so we get 2x squared plus 1 on the top over negative square is same as positive square. Negative square is positive, x squared minus 4. Okay, this is the same function as original, so replacing negative x does not change anything, we get fx back. That means the function has y-axis symmetry. These functions are called even functions. Okay, if we had negative of the original function, then the graph would have origin symmetry. If we get something not similar to the function or negative of the function, then neither. But in this case, we would say y-axis symmetry. Y-axis symmetry. Okay, next in the guideline we need to find the intervals where the function is increasing or decreasing. Intervals of increase decrease. Okay, now the calculus starts. We need to find the derivative of the function. In fact, the function was given in the question, 2x squared plus 1 over x squared minus 4. So we have a quotient of two functions, so we need to use quotient rule to find the derivative. And using quotient rule, okay, you can work on your own. The derivative comes out to be negative 18x on the top over x squared minus 4 quantity square. Okay, just find the derivative using quotient rule. Now to find the intervals of increase decrease, we need to first find the critical numbers. Okay, for that we set the derivative equals 0. That is, this fraction equals 0. This fraction equals 0 and bottom has no contribution. That implies negative 18x equals 0. Divide both sides by negative 18 times, so x equals 0 over negative 18, 0. So x equals 0 is a critical number. Note that this fraction, this derivative is undefined when x equals plus and minus 2, because x equals plus 2 or minus 2 makes the bottom 0. Okay, so they could be critical numbers, but if you go back, look at the domain, x equals plus 2 and minus 2 are not in the domain, so those are not the critical numbers. Now we do the so-called interval test to find where the function is increasing, decreasing. So I want to write down the domain of the function. So domain of the function is all the reals except 2 and negative 2. Okay, except negative 2 and 2. So we already have, the domain is already divided into 3 pieces. Okay, we have vertical asymptote in fact at 2 and negative 2, and we just found a critical number, that's 0. So 0 is here. So we need to test 1, negative infinity through negative 2, negative 2 to 0, 0 to 2, and 2 to infinity. 4 intervals. We need to test the sign of first derivative. Okay, and we conclude about the function f. We pick a representative, any number in between negative infinity through negative 2, any number, let's say negative 3, and plug that number into the derivative. Negative 3 plug in here, negative 18 times negative 3, positive number, and quantity square is always positive, so the whole thing will be some positive number. So I will just write positive. Same thing here, negative 2, 0, let's take negative 1, plug in to the first derivative, negative 18 times negative 1, positive, quantity square is positive, so this is positive. Pick 1, negative 18 times 1, negative 18, so it will be negative, negative. Okay, that means the function, the derivative positive means the function is increasing on this interval, again increasing, negative means decreasing, decreasing. So we will write the function is increasing on here to here, negative infinity through negative 2, and negative 2 to 0. Okay, we have a vertical asymptote, so we cannot write negative infinity all the way to 0, so we need to write in 2 parts. Okay, negative 2 to 0. Okay, and f is decreasing on 0 to 2 and 2 to infinity. And in part f, we are supposed to find local max min, local maximum and minimum. Looking at this interval test, the function is going up, up, down, down. So it's up, down. So we have local maximum at 0. Okay, so local maximum at 0, 0 is the position, and local maximum value is evaluate the function at 0. Okay, local maximum occurs at 0 and the value is f0. Let's evaluate that. 0, plug in 0 into the function. Here is the function. If you plug in 0, you get negative 1/4. That's the local max, and there are no local minimums because we don't have a situation where function goes down and up. So no local minimum. Okay, and finally we have to test the concavity, AFG, last concavity. For concavity, we want to find the second derivative of the function. Okay, second derivative, that's the derivative of first derivative, and we have already found first derivative here. Okay, here is the first derivative, which is a quotient of 2 functions. So we need to use quotient rule to find the derivative of this function, and once you find the second derivative, you will have, after some work, you will get second derivative 18 times quantity 3x squared plus 4 all over x squared minus 4 to the cube. Okay, now to find the possible points of inflection, x coordinates of points of inflection, we set the second derivative 0. Pretty much we do the same thing what we did in part E. That was for first derivative. Now we want to do for second derivative. Okay, so we want to set the second derivative 0 to find the possible x coordinates of inflection points. When we set the second derivative 0, bottom has no contribution, we get 18 3x squared plus 4 equals 0. Now we want to solve this equation for x. Divide by 18 gone, so 3x squared plus 4 equals 0, and move 4 over, so 3x squared equals negative 4. Divide by 3, so let me pull this down. Divide by 3, we get x squared equals negative 4/3. Okay, which is a false equation. We can never have some quantity square is negative. Okay, even if you take positive number or negative number, when we square we always get positive. Okay, so that means there are no inflection points because we didn't find any x value. But we need to do the interval test because the domain of the function is already broken into 3 pieces due to vertical asymptotes. So negative infinity through infinity, except negative 2 and 2, that is the domain of the function. So negative 2 and 2, we have vertical asymptotes. So we need to test 3 intervals for second derivative. Okay, like in previous part when we were finding the intervals of increase decrease, we do the interval test. Okay, pick a representative here and plug that into the second derivative. Let's take x equals negative 3, plug that into here. Okay, when we plug in x equals negative 3, negative 3 square positive, so everything positive. Negative 3 square, 9 minus 4 positive, so we'll get positive number. We don't need the exact number, but it will be positive. That means the function is concave up. Okay, in negative 2 to 2, let's pick 0 and plug in here 0, so we have positive. 0 minus 4 negative, 4 cube negative, so overall it will be negative number, concave down. And 2 to infinity, take 3, plug in here, you get positive, concave up. Okay, though the concavity changes at negative 2 and 2, they are not the x coordinates of inflection points because negative 2 and 2 are not in the domain. Now with all, and we say no inflection points. Yeah, that was here. I mean, we didn't find any x values. No inflection points. Now we want to combine all those facts what we have found so far and sketch a graph of the function. We've seen there are 2 asymptotes, so x equals 2 vertical asymptotes and x equals negative 2. Okay, since the function has y-axis symmetry, this is y-axis, whatever we have on the right we have to have on the left. Anyway, 2 vertical asymptotes, so va x equals 2, va x equals negative 2. Okay, and we also have, go back, we have horizontal asymptote, and horizontal asymptote is 2, y equals 2 on both sides, so y equals 2. So we have asymptote here, HA horizontal asymptote, y equals 2 in both sides. And we found that the function is increasing negative infinity through 2 increasing, negative 2 to 0, okay, negative all the way to negative 2 is going up, negative 2 to 0 also going up and decreasing, okay, and local maximum is 0, negative 1/4. So this is negative 1/4, just somewhere here, okay, is 0, negative 1/4 origin. So increasing, decreasing. So at the same time, concave up, in the middle, concave down, and this is the maximum, concave down and concave up. Whenever we have two asymptotes like horizontal asymptote and vertical asymptote, and we have a graph concave up, so it has to be here, okay. So the graph, let me draw in different color. So the graph of the function is here, concave up, increasing, and between two asymptotes. Same thing here, between two asymptotes, concave up and decreasing. And in fact we have y-axis symmetry as well, so this is like this one, okay, and in the middle, increasing, decreasing, and we have concave down. So, and this is the highest point, so we have asymptotes. So this is increasing, decreasing, and this is concave down, and this is the local maximum. This is local maximum, and this graph has y-axis symmetry. This side and this side are mirror images. So the graph has three pieces. This concave up graph, concave up, decreasing, increasing. This is concave down, increasing, decreasing, and this is local maximum. We have two vertical asymptotes and one horizontal asymptote. Okay, this is the graph. In fact, you can check the answer by graphing your function in your graphing calculator.